Hello, kids. It's that time again. Time to learn about more sequences. I'm going to do a quick little review of what we learned yesterday. If I give you this algebraic expression, we could put different n values in there, like 1 and 2 and 3. So for instance, if I take 1 and put it in here, you're probably all shouting at me that term for a sub 1 is 7. Very good. And if I put a 2 in here, this time 2 times 2 is 4, plus 5 is 9. When I put a 3 in for n, I get 5 plus 6, which is 11, and so on and so forth. And now we can pretty much feel comfortable knowing that this list makes what's called an arithmetic sequence. It looks like the word arithmetic. But I'm going to show you a slightly different way to generate an arithmetic sequence using a formula, and this is just kind of how it has to be, sadly. I'm going to tell you like it is. If I were to give you this expression, a sub n equals 3 plus the quantity n minus 1 times 5. Let's look at that a minute. Eventually what I'm going to do down here is substitute different values in there for n, like 1. You got to do a little bit of order of operation. So again, when I place a 1 in here, the first thing that happens in this expression is that 1 minus 1 is 0. 0 times 5 is 0. 3 plus 0 is 3. That's the first thing you get. When we place a 2 in there, to calculate the second value, again, we could just kind of race through this. 2 minus 1 is 1. 1 times 5 is 5. 5 plus 3 is 8. The third term, this will kind of tell us a whole bunch. It's annoying. When you put a 3 in there, you get 3 minus 1 is 2. 2 times 5 is 10. 10 plus 3 is 13. So hopefully we can see here you're just adding 5 each time. And in fact, in this sequence, you could state a few things. These are facts of the matter. Your first term is 3, and you would write it like such. Your first term of the A sequence is 3. That, by the way, happens to be located here. That's what that 3 means. Whoops. The other thing we're going to notice, I guess I'll use, maybe I'll use sky blue this time, that what you're adding each time, plus 5, plus 5, plus 5, etc., 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 plus 5 makes 23, and so on and so forth. That's what's called the constant difference. The constant difference for this situation is 5, and that's staring at you right here. Constant difference for this example is 5. So on that note, if they were to write a sequence like this, you ought to be able to tell by sight that that is the first term, and the number you have here, this time I'll use 3 because we're doing that. I know you're thinking that it looks like you're starting with 10 and multiplying by 3. We're really not. What we're doing is starting with 10 and adding several groups of 3. So again, by placing a 1 in there, what you do get here is 0. That negates that turns this 3 into nothing, and your first term is 10. We could just pump out a list if we want. To figure out the second term, you put a 2 here, and now essentially this quotient, or pardon me, that parentheses right there, that group turns into 1. You have a group of 3 that you're adding to 10. If you put a 3 in here, see if that works. That kind of looks like a 3. Now 3 minus 1 is 2. You're adding To 10, you're adding two groups of 3. Two groups of 3 is 6, so you're adding that to 10 and you get 16, and so on and so forth. So the key numbers here are, this is your first term. The first term always goes there, and this is your constant difference. So if I gave you this sequence, this is yet another arithmetic sequence. Let's go 20 plus n minus 1 times 4. You ought to be able to just crank this list out. It's 20, that's your first term. They gave that to us. And then you're adding several groups of 4. So another group of 4, another group of 4, another group of 4, etc., etc., etc. This would also work the exact other way, like such. If I gave you a list, let's say your first term was 12, 17, 22, 27, and you noticed, oh, that looks like it's arithmetic. It looks like our constant difference is 5 and our first term is 12. You could write that particular sequence like this. 12 plus the quantity n minus 1 times 5. What I like to do is predict this term, which looks to be the fifth term. It seems like it should be 32. I'm going to just put a question mark here because we're wondering that. And when I evaluate the fifth term, when I put a 5 here, 5 minus 1 is 4. 4 times 5 is 20. 20 plus 12 is 32. It checks out, it works out. We've determined it. So one more time, if we gave you a list and it appeared to be arithmetic, what you would notice is they would give you the first term, comma, the second term, comma, the third term, comma, the fourth term. They would give you these as real numbers. What are we adding each time? You're adding d, which is the constant difference. And if you think about it, to get to this missing term, you started with your first term here and added d again, added d again, and added d yet another time. This is what's called an explicit formula. Would be written like this. This is the generic way to write it. Times d. And oh, by the way, you could actually have a list that starts at 100 and works its way down. You don't say that you don't say you're subtracting d. What you do in this instance is say I'm starting at 100 and I'm adding several groups of -3. You just note that your constant difference is negative. All right. So now we're going to dive into the geometric sequence that's related to that. Remember, this is the one where you basically you're multiplying from term to term. We start at 5 and constantly double. It would be written like this. There's kind of the same rationale by why you're subtracting 1 here, but I'll just go through a few of these. If you wanted to figure out your first term, you would place a 1 in for n. That math right there would turn that into 0. 2 to the power of 0 is 1, and 5 times 1 is 5. Maybe I'll make a list here off to the side. Your first term is 5. When you put a 2 into the sequence, the math you do first is this exponent. 2 minus 1 is 1. 2 to the power of 1 is 2. 5 times 2 is 10. So the second term is 10. To determine the value of the third term, you put a 3 there. And hopefully it's pretty obvious that you're just kind of including more and more factors of 2 now. 3 minus 1 is 2. 2 squared is 4. 5 times 4 is 20. And this certainly looks like that these are all multiplying by 2. What we say in this case is that you have a constant ratio. This means that if I take the ratio of these two terms, 10 over 5, or the ratio of these terms, 20 over 10, or in fact the ratio of any consecutive terms, they all give you your constant ratio of 2. So in this instance, your first term was 5. That's located there. Your constant ratio of r was 2. For this one, I'll give you another geometric one. I'm going to start at 100. That's your first term. This time your constant ratio, what you're constantly multiplying by, is half. So to create a list, it's not that hard. You can either put You're counting numbers in here. Put a 1 in there and get 0, and anything to the power of 0. You can evaluate this manually, or just note. If we're going to create a list, your first term is 100. The next one you'd multiply by a half, multiply by half again. You're continuously multiplying by half. This is about the point where I fail multiplying by half, so we're going to take a break. To look at another reverse situation, if I gave you a list of numbers, 6, 12, 24, 48, and we said, boy, it looks like you have a first term and we're constantly multiplying by 2 to get from one to the next. That's all you need to know to write your expression. G sub n equals your first term times your constant multiplier r to the power of n minus 1. Sometimes the constant ratio is kind of hidden in there. For instance, they gave you a first term of 5 and then 8, and they told you that it was a geometric situation. To evaluate r, you would simply take 8/5, which is 1 3/5 or 1.6, and that's okay to have those type of decimals. They can be, it can actually be a wide variety of numbers. You tend not to see 0 or 1 because it just is kind of pointless. Then to figure out the third term, you would multiply 8 times 1.6, etc., etc., etc. But if you were writing the expression, you would write G sub n equals your first term times your constant ratio to the power of n minus 1. This stuff will pop up on page 6 of your assignment, by the way. And if by chance this was negative and negative, you would still, if all your terms in your expression were negative, you would still have a positive constant ratio. It just means that your first term was negative. If they alternate, and I'll show you what I mean by that. If the terms of your sequence alternate from 2 to -4 to +8 to -16, so on and so forth. If I look at the ratio generated here, that's -4/2 equals r. You can have a constant ratio that's negative. So in this instance, your first term is 2, and your constant ratio is -2. All right.